Hello everyone, my name is Ric, and I'm presenting some of our latest work on forming fiber-steered preform towards fast and reliable production of complex composite parts. Starting with a little background information, as we know, automated fiber placement AFP allows for efficient deposition of composite prepreg material at large scale in a reliable and reproducible way while keeping human effort to a minimum. AFP combines many processes into a single step. As a result, many machine parameters need to be adjusted, and all these parameters can affect the final quality of the layup. Therefore, this technique is not perfectly suited to manufacture small, medium parts with complex geometry, as deviation between as designed and as manufactured parts are almost inevitable, as well as the occurrence of process-induced defects. An alternative manufacturing technique to AFP was proposed in this study, and it can be summarized as lay flat and form. Fiber tips can be laid continuously in flat with designed steer paths and shape using continuous toe shearing CTS techniques. This tailored 2D preform can be manufactured to desired 3D shape by forming, where automated ply deposition and forming are combined. The way to get tailored 2D fibered paths and shape was using virtual unforming simulation. This numerical tool was developed in this work and validated by experiments. To demonstrate the process, we started with a doubly curved twisted plate, with overall dimension shown in the first figure. An overview of Abacus double diaphragm forming model is shown in the middle. The way to have unforming simulation is simply fully reverse the forming process by reversing the nodal displacement history of the two diaphragm models. Several post-processing steps were used to convert the 3D CAD model of this twisted plate to a finite element model with elements and material orientation aligned to the designed fiber paths. During unforming simulation, this twisted plate model with its designed fiber paths was inserted between double diaphragm and was unformed back to flat shape, with fiber paths transformed from 3D to 2D. After the unforming simulation, this 2D preform model with tailored fiber paths was then post-processed to a stage that we can extract a representative single fiber path out of it for manufacturing. And this step corresponds to the second step of the proposed manufacturing method. This single fiber trajectory was then fed into a CTS machine for preform production, as shown in this video. Two parallel 100 mm wide tapes were laid with marked lines for tracking purpose. After we have the physical 2D flat tailored preform, it was then subject to a forming process. Figure A on the left shows fiber-steered preform that was formed onto the twisted plate mold. The same forming test was performed with a UD prepreg sheet, as shown in Figure B. Comparison between Figure A and B shows that when using UD preform, a large amount of material need to be trimmed off to feed the surface, which leads to material wastage. The UD preform also has a reduction of continuous spanwise fiber running from the left to the right of the shape. However, in the formed CTS preform, the amount of continuous fiber was greater and the trimming could be kept to a minimum. Figure on your right shows a more quantitative comparison. Deviation of fiber trajectories in the designed fiber paths in the FE forming simulation was compared with the physical demonstrators. Figure A is comparing as manufactured steered preform to the as designed FE model, and Figure B compares the as manufactured UD preform to the as designed FE model. It can be seen that fiber angle deviation observed over most of the area of the steered preform was below 5 degrees, and it is much less than its UD counterpart. These demonstrate the advantages of the steered preform in the forming of complex shape. It was also found that the steered preform appeared to be easier to form, which suggests that in the case of more aggressive mold surface profiles, this technique may help to reduce the forming-induced defects. Thank you very much for your attention. More information can be found in the following paper. If you have any questions, please feel free to contact me, Ric Sun, at bristol.ac.uk. Thank you.